Okay, so how are we all doing this morning? Good? Bad? You made it to class on time, that's something. Anybody been to their tutorial yet this week? How did that go? Good. Did you get to see anybody else's games or demonstrate your game? Yes? No? Yeah. Okay. Good. So if you haven't been to your tutorial yet this week, bring your game along, whatever is made of it, or go and have a look at what other people are doing. The woman who organizes the tutorials and also coordinates the marking of your assignments has offered and is willing to organize a showcase during one of the later tutorials where people who are interested can come stand at the front of the tutorial room and demonstrate their game to the rest of the class. So you get 5 minutes or so to show them the features of your game. So I guess my question is there anybody who would be interested in doing this in a later tutorial? Yeah, a few people. Is there anybody who would be interested in seeing other people's games in a later tutorial? Okay, so there's a bit of an asymmetry there, right? Nobody wants to show their game, but everybody wants to see what other people did. I think what typically happens is you get a few people who want to show off their work. They do that, and then the people in the audience say, hey, that was really crappy. I think mine was better than that. So they say, hey, I want to show off mine too. We'll probably organize something like that a little bit later, after assignment 8 is well and truly over, and even if people were still hunting down bugs at the time of submission, we'll give them a week or two to totally clear them out. Okay, so at the end of last class, we had been doing recursion. We've been looking at recursion and trying to understand the recursive stack and looking at some good examples of recursion. So we had seen the quicksort function, which is really easy. It sorts an array of elements. If the length of the array is less than or equal to 1, then it's really easy to sort. You just return the original array. It's already sorted. And otherwise, you pick a random element and you partition the array into the stuff that's smaller than that random element, the stuff that's equal to that random element, and the stuff that's bigger than that random element. And then you recursively sort the first part, that's the smaller stuff, and you recursively sort the last part, that's the bigger stuff. And if you take those three results and concatenate them, you get the original array in sorted order. So that's a good example of recursion. And then we looked at another example, which is this notion of computing the power set. But we were running out of time, so I just coded it really quickly and didn't explain much about how it works, and didn't give a great definition of the power set either. So first, what is this? What are these power sets? So if I take a list, so you can think of this list as a set, or just think of it as something that the order doesn't matter. So in this case, lists actually have a specific order associated with them, but pretend that the order doesn't matter, so that this is just three items. And then I ask you, what are all the ways of taking a subset of these three items? So making a choice from these three items. So for example, I could choose all three of them. That's one of the ways. I could choose any two of them, or I could choose only one, or I could choose none at all. And so for example, for the choices that involve only one, there's three such choices. The one where I only choose one, the one where I only choose 2, and the one where I only choose 3. And so this power set function is supposed to generate all these possibilities of choosing these things. So here, for example, there's the power set of 1, 2, and 3. There's the option of choosing nothing. That's given by this empty list over here. The option of choosing only 3, or only 2, or 2 and 3, or only 1, or 1 and 3, or 1 and 2, or 1, 2, and 3. The whole set. Okay? And so here there are 8 options that came out of this, 8 different ways of choosing a subset from A. So why is it 8, I guess, is the real question. And the related question is, well, what if I give you 4 choices? How many different subsets will I get? 16. So what's the reasoning for that? So 2 to the power of the length. And why? Can you explain in words why the number of choices should be 2 to the power of the length? So there's sort of an easy way to see it, and that is, if I want a subset of a given set, then I can make any such thing by taking the items in the set and deciding one at a time whether or not it's going to be in the subset. Right? So I take the first item, item 1, and I have a choice, and I can decide item 1 is in the set or it's not in the set. So there's 2 options for item 1. Now I move on to item 2. I can choose whether it's going to be in the subset or not in the subset. So there's 2 options for that, which means that together for 1 and 2, there's 4 possible options, 2 times 2. And now I move on to item 3. There's 2 possible options. It can be in the set or it could not be in the set. And so now that means 2 options for 3 plus times the 4 options for the first 2 gives us 8. And then finally, for item 4, we can choose for it to be in the set or not in the set. And that gives us twice as many options as we had for 3, which was 8, so 16 different ways. And the code for generating this power set actually works exactly that way. So it does the following. It takes the first item away. So it takes item 1 and gets rid of it, and then generates all of the power sets, the power set for everything else. So, right, remember A at 1 colon here, that's the slice which discards everything but or discards the first item and keeps everything else. It generates the power set for that. And it calls that S. And now, there's 2 options for item 1. Either it could be in this set or it could not be in the set. So if I look at all of the power set that I get back, well, if I don't include item 1, then that lists all the ways of doing those things. And if I do include item 1, well, this generates another list, which is everything that was in the power set of the stuff that doesn't include the first item, and then you add the first item to it. And you can see, actually, the way that this worked, when I took the power set of 1, 2, 3, the first thing I get is 4 sets, none of which include 1. And the next thing I get is 4 sets, all of which include 1. Okay? So that's the way this thing was generated. It took the first thing it did was computed the power set of 2 and 3. That gives me these 4 sets here. And, well, those are included in the power set of 1, 2, 3 because they're all subsets of 1, 2, 3. But then for each of those, there's a corresponding set that also includes 1. And that's these 4 sets here. So that's the way this code works. You take the sets that don't include 1, and then you take the sets that do include 1. All right? So what's a a use of these power sets, or why would you ever want to do this? Well, it turns out that there are some problems where the easiest solution, and sometimes even the most efficient solution, is just to try everything. And one of those problems is what we'll call the knapsack problem. And here's the story behind the knapsack problem. You are a master thief, and you manage to break into Fort Knox. So Fort Knox is where they keep all the gold, and you want to steal a lot of this gold. Yeah. Yes, I am. Yeah. So you want to break into Fort Knox, where they keep all this gold. Now, in your break-in, you had to crawl through some tiny tunnel space or something, and the best thing you can't carry a lot with you. You can bring a knapsack with you. That it's a pretty good knapsack. It can hold something like I don't know, 300 pounds of gold. Hopefully, you can carry that. But if you put any more than 300 pounds of gold in this knapsack, the straps are going to break, and you're not going to be able to do whatever you need to do to get out with your gold. So you want to get 300 pounds of gold, but not more than that. If you put more than that in there, the straps break, the knapsack falls apart, and you're not really able to carry any of this stuff out. Now, in Fort Knox, gold is stored in whatever bars of different sizes, and shapes don't matter. All we care about is the weight. So they have different sizes. Some weigh more than others. And so now what you want to do is, given all of these bars of gold that you have access to, find a bunch of them that add up to exactly 300 pounds. Not more, and ideally not less. So in the knapsack problem, you're given a list of weights. These are the weights of the bars of gold, and a target weight, which is, in this case, 300 pounds, what the most you can carry in your knapsack. And you want to know, can I make this target weight out of this list of weights that I have here? Okay, so the weights given by A. So back in the language of Python, you're given a list A of numbers, and you want to know if there's a subset of those numbers which add up to exactly t. So how do we solve that? And what does that have to do with power sets? Yep.
We use the power set to have n for each, so we can have combinations for all A and just sum each element in the power set.
Yeah. So it turns out that this knapsack problem is actually a really hard problem, meaning that it's hard to do it efficiently with a computer. And the solutions for this problem, in the worst case, there's not much more you can do than trying every subset of elements to see if they add up to exactly t. So what we can do is, well, we want to know, is there some subset of A which adds up to exactly t? So let's say take PS will be the power set of A. And now we'd like to know the ways we could, the subsets like this that sum up to t. So what we'll return is a list, and it will contain all of the sets for S in the power set if the sum of S is equal to t. Okay. So once you have this power set thing, this problem becomes trivial because you just enumerate all of these, all of the possible solutions and check to select only the ones that actually work. So let's try that. So let's take a set A is equal to 100, I don't know, 50, 20, 10, 5, 1, 25, 1. Okay, so there's a list of numbers, and I want to know, can I make 175 out of this list? So try that. Why did I write subset sum? Oh, it's not called subset sum, it's called knapsack. And this thing returns, yes, you can make it, and you can make it this way, by taking 100, a 50, a 20, and a 5. Can I make 178? No. Can I make 179? No. Can I make 180? Yes, by taking 100, a 50, a 20, and a 10. Can I make 180 and 50 cents? No. Can I make 180 and 35 cents? Yes, by taking these things here. Okay. So this will solve this this knapsack problem for any target value and any set of elements. Now the problem with this solution is it does this by generating the power set, and while we decided that the power set of n elements has size 2 to the n, so for example, if you break into Fort Knox and there's 30 pieces of gold there, or let's say 32 pieces of gold there, then this solution works by trying 4 billion different combinations to see which ones add up. So you better bring your pocket calculator with you if you're going to try and do this for your Fort Knox robbery, because you're not going to be able to do it by hand. Okay, so any questions about that? Good. So now what I want to start looking at is, so now we're all on the same page, hopefully, with recursion. We all have a pretty good idea how it works. There's this recursive stack. You have to be careful with recursion that you don't make a recursive stack that gets too big, otherwise you blow it up. And now we're ready to start looking at really algorithms and analyzing their running time. So one thing I'd like to introduce you to is in Python, there's a module called timeIt that contains a function called timeIt. From timeIt, import timeIt. So there's a function called timeIt in there, and it's useful for looking at little pieces of code to see how long they take to execute. So for example, how long does it take to execute 2 plus 2? So if I give it something like this, the string 2 plus 2, this is a piece of Python code, right? This is 2 plus 2. And timeIt will execute that piece of code 1 million times and tell you how long it took. So how long do you think it's going to take to execute 2 plus 2 1 million times? An hour, a second, half a second, thousandth of a second. So it takes about 3/100ths of a second to do that 1 million times. If I want to assign it to a variable, that doesn't take much longer. If I change addition, well, yeah, let's not play with that now. Maybe we can. If I change addition to multiplication, nothing really changes much there. If I execute two things like this, y equals 2 times x. So now it'll execute these two instructions, x equals 2 times 2, y equals 2 times x. Takes you know, a little bit longer, but not a ton of time. So around 1/10 of a second if you do it repeatedly. Okay. So one thing we're going to want to do is be able to predict how our functions will, how long our functions will take to run. And well, the reason we'd like to do these predictions is because for bigger problems, you spend some time coming up with a solution to the problem, and if it's a complicated problem, it takes a fair bit of time to actually code that solution. And you would like to know in advance whether this is worth spending the time coding it or not, or because if it's going to be slow or if it's going to be fast. And you know, if it's going to be slow, don't waste time coding up a slow solution. Spend a little bit more time thinking about how to make a fast solution. So what are the things that are fast for computers to do? Well, these basic operations like this are generally fast. And fast means they take a few cycles of computer time. You know, computers operate at clock speeds that are measured in gigahertz, so that means they do something a few billion times per second. There's a cycle that happens, and these basic operations take a few of those cycles. It's usually some constant number. You know, maybe the constant is, if you're using Python, maybe the constant is 500. It takes 500 cycles to multiply two numbers and assign them to a value, to a variable, like we're doing here, and here. And, well, we'll say that. Maybe it takes 500 cycles. I don't know. It takes some number of cycles, and we can get an estimate by using time it. And we can do lots of things this way. Instead of multiplication, we can see maybe is division a bit more expensive? It's about the same. What if we do floating point division? Then it's a little bit more expensive. But all of these things are still pretty fast, right? This code is being executed 1,000,000 times, and it's still taking only a little more than 1/10 of a second. So we could be executing it, you know, 10 million times in a second almost. All right. So things that can be done quickly are any of these basic arithmetic operations if they're working with integers or floats. Can you think of any of these operations which don't work with integers or floats, or would give you something other than an integer or a float and might take longer? How about this? So let's time that. X to the 10. Let's try x to the 100. That takes quite a bit longer, right? So if I take x to the power 10, then, you know, this thing takes 16 1/100ths of a second, and if I take x to the 100, suddenly now it takes 2.3 seconds. How about if I take x to the 1,000? So certainly 2.3 seconds has elapsed by now. So this seems to be taking a long time. Why is this exponentiation taking so much longer than anything else? Is it an operation that gives you an int or a float? So what it gives you is a long. And so Operations on longs take time that's somehow related to how big they are. And in this case, this is a big one. It has, I don't know, 300 or so digits. And so, so there you go. That's why this one takes longer. And if you look at how long it takes, it's basically seems to be related to the number of digits, right? Here, x to the 10 is, you know, fast. X to the 100 takes about 10 times as long. X to the 1000 takes roughly, again, 10 times as long as x to the 100. So this seems to be related to the number of digits. So in general, basic operations like addition and multiplication, subtraction, all the BEDMAS stuff, they're pretty fast unless you do something that makes a long integer, in which case they start taking time that's related to how long this integer is. And so they can get slow. What else? So this timeit function has a couple of optional arguments. So this code that executes here, this x equals 2 times 2, is done, it's treated as a program all by itself. It just gets executed, you know, 1 million times as a program all by itself. Sometimes you need to set stuff up for this program to run, in which case you can provide a second argument, like this. So when I call timeit this way, it will execute this code once. It'll set a equals 2, b equals 3, and then it'll execute this code 1 million times and tell you how long that took. Because, you know, some things you want to time need some setup. They need to access some variables. You don't care about the setup time. You care about how long this bit of code took to execute. So, so there, this works. If I had left this out, for example, I'll get an error that says this name B is not defined. Okay, so questions about how timeit works? Yep. Yep, you can call a function, but remember this thing is a program that lives all by itself. So I can call, you know, f of x or foo of x if I have a function called foo, but I'll actually have to define that function here. X to b. And I can't call foo of x, I can call foo of 2. So this will execute the function foo 1 million times with the argument 2, and here's the definition of the function foo. It just returns 2 times x. Yep?
Is there a way to run on the whole program and see how much time each line takes?
Timeit doesn't do that, but if you look in the timeit module, there's a thing in there called a timer that you can wrap around sections of code to see how long they take in your program, or you can use other time functions to do that. But no, timeit is not it's not what's called a profiler that will tell you what the most time-consuming parts of your code are. I think there probably are profilers for Python, but this is just for testing really basic things to get a feel for how much things cost. Okay, so again, you can call a function, and you know, something else. Calling a function takes a little bit of time, but it's not a huge amount of time. It's comparable to what happens when you add a couple of numbers together. You know, it's 5 times as much, but it's not 1 million times as much or 1 billion times as much. Other things that you can that don't take long. So let's say in my setup, I define a function or an array which contains 10 elements, and I'll define an index I, which is the length of A divided by 2. And I can say something like x equals A at I. Okay. So So this is the setup, create an array of length 10 and define this index I, and then the code that I want to see how long it takes is to check x equals a at I. Very fast. Okay. So that's for an array of length 10. What if I increase the length of the array? Is this going to be fast still? So what if I use an array of length 100 or even 1,000? Any guesses? So arrays, and in all languages and in Python they're called lists. You can access any item of an array in basically the same amount of time. So here's an array of length 1,000. It still takes about the same of time to access the 500th element as it did to access the 5th element in an array of length 10. An array of length 10,000, nothing changes. An array of length 100,000, nothing changes. Even an array of length 1,000,000 still takes the same amount of time to access an element. So accessing an element in an array, looking at its value, no problem there. And the same thing if I do, rather than looking at its value, if I change its value, that takes a little longer, but it has nothing to do with the length of the array. Doesn't matter if it's an array of length 1,000,000 or an array of length 10, it takes about the same amount of time. Okay. So accessing items in lists is really fast. It's as fast as accessing a variable, basically. So that's another thing, that its time doesn't depend on the length of the list. Okay. Something else we've seen are sets. So let's make a set is out of the range 10. So this will create a set with 10 elements in it. The elements are the integers 0 through 9. And let's say, again, I is equal to the length of S divided by 2. And I can ask, or let's call that thing X. So what are the operations I can do on sets? So I won't continue until somebody tells me something I can do with a set.
Iterate through it?
You can iterate through it. Okay, let's try that. For X and S, just do nothing, pass. So this will just iterate through it and do nothing for each thing. So that takes a little more than half a second, 0.6 seconds, to do that 1,000,000 times. What if I increase the size of S? What's that? Nope. So now it takes a lot longer. If I increase the size of S by a factor of 10, it seems to take, well, not exactly 10 times longer. That would be 7 seconds, but a fair bit longer. And if I increase it by a factor of 10 again, we're probably going to be looking at something like 40 seconds to do that. Now, that makes sense, right? So this is a for loop in which X has to take on all the different values in the set S. So really, X will be equal to 0, X will be equal to 1, X will be equal to 2, X will be equal to 3, all the way up to the length of S minus 1. So that should really take time that has something to do with the length of S, right? You can't count up to 1,000,000 as fast as you can count up to 10, or you can't assign, almost exactly, well, not almost exactly, but pretty close to 10 times the time it took to do a range of 100. So iterating over a set takes time that's related to the length of the set. And really that's just because the number of things that happen is the length of the set things, right? X takes on that many different values, so it can't go faster than that in some sense. What else can you do with sets? What are the main things you do with sets? Yeah. Check if something is in the set. So you do that by asking the question, is X in S? So if I do that on a set of length 10, that takes about 1/10 of a second to execute. On a set of length 100, the running time is indistinguishable. On a set of length 1,000, takes maybe a little bit longer. On a set of length 10,000, still the same. 100,000, still not really much slower. Even a set of size 1,000,000, not really much slower. Okay. So sets, you can check anything, check if something is in the set in time that has nothing to do with the size of the set, really. Doesn't matter if the set contains 10 elements or it contains 1,000,000 elements. You can check if something is in there and the time is not related to the size of the set. What else can you do with sets? Yep. Well, that's really what's happening here, right? We're checking if some value X is in the set. So is there a value X in S that is there a value in S that's equal to X is really what this is doing.
Was it the equals supposed to be slower?
No, I mean it's pretty fast even for 1,000,000 things. The other two things you do with sets are add and remove. So for example, we could say remove X and then add X. And so from the set, remove X and then add it back. How long does that take? Again, super fast. And that's true for a set with 1,000,000 elements. If I reduce the size of the set, it doesn't really get any faster. So sets are these incredible structures that you can add or remove things and check if something is in there in time that has nothing to do with how much data is in there. So they're really good for that. Lists or arrays are these incredible structures that can be huge and that you can access the element at any position in time that has nothing to do with the size of the array. So if I have an array with 1,000,000 elements, I can access the 500,000th element very quickly. If I have an array with 1,000,000,000 elements, I can access the 500,000,000th element very quickly. And sets are similar, but you don't access elements by position. You can access them by value, add or remove them, whatever you want. Okay? So all things that don't take long are, let's make a list of them now. So these are things, operations that execute in constant time. We saw calling a function. The actual act of calling the function doesn't really take much time at all. If the function does something inside of it that takes time, well, that's another story. Basic arithmetic on ints and floats, but not longs. Accessing an item in a list/array, modifying an item in a list or array. So these are all somehow constant time things, really, really efficient, and checking if an item is in a set, and adding to or removing from a set. Okay. So these last four here are interesting because arrays and sets can have different sizes, but the size doesn't seem to really matter in terms of the running time. Things that can take long. Well, we've seen one of those. Iterating over a set. In fact, the same thing happens if I iterate over an array or a list. This takes time proportional to the length of this thing. Proportional. Okay, let's look at some other things that take time. So we saw that for sets, checking if an element is in the set doesn't take any time at all. I mean, it takes a small amount of time independent of the size of the set. What if instead of a set I use a list? So here I create a list of length 10. I take x equals 5, and I check if x is in A 1,000,000 times. Is this fast or slow? Fast. What if I increase the length of the array to 100? Doesn't get any slower. What if I increase the length of the array to 1,000? Doesn't really seem to get any slower. But I've been telling you all along that it takes a long time to check if something is in an array. Why is this always fast? Yep. Because it's what? Yeah. So the way checking if something in an array works is it just starts at the beginning of the array and starts looking for it. In this case, if I'm always searching for 5 and the array is made using this range function, then the 6th element that I look at is actually the one that I find. It doesn't matter if there's 1,000,000 elements in the array. After looking at 6 of them, I'll find the one that I'm looking for. And, we can even check that. So there's an array of length 1,000,000, doesn't really change things. But if I do something else, I look for, let's say, the length of the array divided by 2, then that starts out as 5 when the length of the array is 10, but when the length of the array is 100, it's 50. And it takes significantly longer, something like 10 times longer. If the array has length 1,000, it's going to take probably around 15 seconds because it has to look through 10 times as many elements as if when the array is of length 100. Okay, so searching for things in an array using this is not a fast operation. Unlike a set, where it didn't matter how big the set was, we could look for things in a list. If the list is big and you get unlucky and you don't happen to find it right near the beginning of the list, which is what happens most of the time, then you take time that's proportional to the length of the list or the position where you find it. Checking if something is in a list/array. there's a confusing sentence, but I think we know what it means. If I look for something in a list, if I don't find it, I'll actually go through the whole list, so then it takes time proportional to the length of the list. And if I do find it, it takes time proportional to the index that I found it at. Okay, so looking for something in a list takes a long time. We saw that that accessing the elements of a list is fast. So, right, we saw this x at I, or sorry, not x at I, a at I. That's a fast operation. How about just making a list? So, the range function makes a list for us. How long that takes, does that depend on the length of the list or not, do you think? No? I'm afraid it does. So making a list of things takes time that's proportional to the length of the list that you're making. And so, and there's many ways we can do that. Range is one way to make a big list. We can also create a list of length 1, that has one item, and then multiply it by an integer. That will give us a list of length 10. In this case 10, but if I multiply by 100, it's going to take 10 times as long as it did for a list of length 10. Yep.
But in all the testing previously, you were using the solution or the depth, and you were varying the value. Why wouldn't that affect the?
Because the timeIt function has these two arguments. There's this code here that gets executed once and doesn't get timed. And then there's this code here that gets executed 1,000,000 times and does get timed.
So you create that one first, and then after that,
Yeah.
test.
So it basically, the timeIt works like this. It executes this code, then it checks the time, or it starts a timer, and then executes this code 1,000,000 times. Once that's done, it stops the timer and reports how long that took. So this first piece of code actually doesn't matter how long it takes. That won't affect the result of the time, of the recorded time. Okay. So making a list, this takes time proportional to the length. And we see that there's other ways to make a list. We've seen list comprehensions as well. So where you do something like x squared for x in A. And if A is a list of length 10, that's reasonably fast. But if I make it a list of length 100, it's going to take 10 times as long again. So making a list, and that includes the range function. It includes multiplying a one-item list by an int, and that also includes list comprehensions. All right, and we've seen iteration. So now we have a fairly good idea of, things that take constant time, that's, independent of the size of the list or array, and then things that take time that's proportional to the length of the list or the array. And now we can start making some functions and analyzing them even beforehand to see how long that they will take. So for example, here's a function that takes one argument n. Presumably n is an integer. And the time that this takes to execute, does it depend on n or not? If n is a small integer or a float? No, not really, right? So it doesn't matter if so let's time it foo of 50. So it doesn't matter if I do foo of 50 or foo of 500, takes about the same amount of time, and so does foo of 5,000. So this does a bunch of operations. You know, we're calling a function. We saw that that's something that takes constant time. We're doing a multiplication. We saw that that's something that takes constant time. We're doing an addition. That also takes constant time. A division and a subtraction. All of those things take constant time. So you add all of those up, and all of that just adds up to a few cycles, just independent of the value of n here. As long as n is not something crazy like a long int, this is fine. Okay. Here's another function. It computes the sum of 0 to n minus 1. Not the shortest way of writing it in Python, but nevertheless. So the running time of this function, if we're going to estimate it, does it depend on n? Yeah. So I see here this function has a statement that sets c equal to 0. Well, that doesn't really depend on n. That's a constant time thing. We saw that accessing and changing variables doesn't take any time at all. But I see a loop in here. And this is a loop that goes over a range n. So a couple of things. Just creating this range takes time that's proportional to n. And then this loop iterates that many times, and it executes this piece of code. Each time it does that, it takes constant time, so this is going to be some constant times n time. And indeed, well, I won't do it, but I won't do it because it takes a little effort to time this much code. But indeed, this takes time that's proportional to the length of this thing. And it doesn't matter if I try and cheat my way around it by making the code shorter. So for example, we saw that there's other ways to do this. I could say reduce lambda xy plus y. This isn't really going to change it. So this does the same thing as this does. It adds up all the elements in an array. But this function still has to create an array of length n and then add up the elements in it. So it's still going to take time that's proportional to n. So it's shorter code, but it's not really any faster or any slower. It still takes time that's related to n. So let's let's just import that and see, you know, bar of 10 is quick, bar of 100 is quick, 1,000 is quick. So all of these things are quick if you only execute them once, but, well, once you start getting up to 1,000,000 elements or 10 million elements, you see that it's actually now taking some time to do this. And bar 2 might be a little bit faster, but not a ton. In fact, it looks like it's slower. How about this? That's not even true. Just, let's say bar I. So, how about this code? So, it takes an argument n, sets c to be a variable, and then it starts iterating over n. It iterates over an array of length n. And at each iteration, it computes c equals c plus bar of I. Let's make it a little bit clearer. Let's compute bar of n first. At each iteration, it computes this. Okay. So the time that this takes is, I mean, it's certainly related to n, because we iterate over a range of size n. Now, is it just proportional to n, or is it even bigger than that? Yeah. So this function here takes time that's proportional to n. So we'll put that in the comments. This takes time proportional to n. And if we commented all these, this takes constant time. This takes constant time, but gets executed n times. So that's why the whole thing takes and takes time proportional to n. Now, if we write all the same stuff down for this function, we get that this takes constant time, this takes time proportional to n, and this takes time proportional to n, and gets executed n times, right? Because bar is this function that takes time proportional to n. So each time I call bar, it takes time proportional to n, and I do that n times. So this actually takes time proportional to n times n, or n squared. So we saw that bar, you know, bar of 1,000,000, even bar of 10 million takes time, takes some time, but it's, you know, reasonable. It gets done in a second or two. Now how about foo bar? Oh, I see. car forgot to return a value. So foobar of 10 is pretty quick. Foobar of 100 is pretty quick. Foobar of 1,000 is pretty quick. But 10,000, we run into problems. Took a little while. And how about 100,000? So A, right, we keep, the size of A keeps getting smaller and smaller each time we call this thing, until eventually the size of A is 1, and the next time we call it, the size of A is 0. And that's what happens here. A is an empty list, and we're asking for its 0th element, and that's an index error because there is no 0th element. There's no elements at all. And that's because we're writing a recursive function, and we didn't include a base case. So we have a case where sometimes we get lucky and we find what we're looking for, so it doesn't crash, but we didn't include a base case. And so what is the base case here? When do I know x is not in the A at all? Yeah. Yeah. So if the length of A equals 0, then I can safely tell you that x is not in A. So this will then tell me whether any element is in this set. Okay, so let's try and analyze this thing to see how fast it is. So one line at a time. Checking if the length of A is 0. How long does that take? Does it have anything to do with the length of A? No. This just takes constant time. If we return false, that also takes constant time. What about this? This is just basic arithmetic. We take the length of A, we divide it by 2, we assign that to I. That's one of those things that takes constant time. Checking if x is less than A at I, that's an array index. That takes constant time. And an arithmetic operation, a less than operation. So that's also constant time. Similarly, this takes constant time. And this takes constant time. So the only question marks here are these recursive things. So from what you see here, how long does this take? So what are we doing here? We're making a recursive call, and we're making a recursive call on what? X. And what about this thing? Yeah. It's an array that's half the length. It's a slice. How long does it take us to make that slice? Yeah. So making the slice takes time proportional to the length of A. That's bad news, right? If making this slice, because this is a slice that contains half the elements in A, if that takes time that's proportional to the length of A, then I might as well have just looked through all the elements of A to look for X. I mean, maybe this could potentially be twice as fast, but it's not going to take something like constant time. I mean, it's not going to be more than twice as fast as just looking through the whole array. In fact, it might even be slower because we then have to make a recursive call. So what we'll have to look at next class is a different way of doing this where we don't have to take a slice this way. We'll have to restructure this so we don't take this full slice.
Yep.